Okay. I hope the concept is starting to click by now, the complex analysis. Today and Wednesday and Friday, we will talk about power. Okay. There will be many power terms that I want you to start listening very carefully from today. Otherwise, you'll be confused. What do you know about power so far? Let me ask the question in this way. Whenever you see power in the statement of the problem, or you hear power, what two variables or what two quantities you go for? Voltage and current, right? Okay, so that is something that I want you to understand from the beginning. Now, the power that we've been dealing so far was mainly related to DC circuits, so nothing was time dependent actually. So you had some voltage, you had some current, you multiplied them together and you got your power. Now, the first power term or the first concept in power that we're going to talk about today is instantaneous power. And why do we need to talk about that? Because starting from the third part of the lecture, you are becoming more familiar with time-dependent sources, like the sinusoidal or cosine excitation sources. For example, let's talk about this RLC network made of resistors, capacitors, and inductors. You have some sinusoidal sources connected to that, and it's going to push some current into the network. Now, these are the most general form of voltage and current that I can use. A voltage with some amplitude, some phase, current with some amplitude and some phase. And if you notice, the frequency is the same, okay? So these are the most general form that I can write voltage and current. And remember, in this course, whenever your voltage has some frequency, the current will also have the same frequency. Every quantity in the circuit will have the same frequency. Frequency is not going to change. That's not the concern of this course, okay? So frequency is constant. Now, is there anything new about this equation? PT is equal to VT/IT, just multiplying voltage and current and multiplying two cosine functions. Now, the first concept, as I mentioned, is instantaneous power. What's the meaning of instantaneous? At a specific instant of time, right? So technically what we're saying is that P is a function of time. That's why you see PT. And at any moment, it's going to have some value. Okay, that's why we call it instantaneous, time dependent. Now, let me ask you one question. PT is a function of time. Can you tell me what is the amplitude of PT? What is amplitude defined as? Amplitude is the thing that is multiplied by a single cosine. Not by cosine squared, or not by a product of cosines. One single cosine, whatever comes before that, is your amplitude. So do you know what's the amplitude of PT? No, we don't have it based on this equation. So that's why we don't really like products of cosines or sines in our expressions, because they are not intuitive. We cannot understand the concept of amplitude or phase instantly. So there is a trig identity, very famous one, that changes the product of two cosines into sum of cosines, okay? It's called product to sum conversion. So cosine alpha times cosine beta is equal to 1/2 cosine of the sum of angles plus cosine of the difference of angles, okay? That's a very famous trig identity. Let's apply it to this guy, to the original equation, and see what it gives us. So I'm going to call this thing alpha and this thing beta. So do you agree that if I write this, it's going to be 1/2. I don't care about the coefficients. I can just bring them later. But what is important is that the first term is going to be cosine of alpha plus beta, and the second term is going to be cosine of alpha minus beta, right? So what is alpha plus beta? It's 2 omega t plus theta v plus theta I, right? Here. And what is the difference of alpha and beta? Is omega t's cancel out, it's going to be theta v minus theta I, right? Exactly as you have it here. Okay? So this is exactly the same instantaneous power. The only difference is that I changed the product to sum. Now this is much more interesting and intuitive. Now let's talk about different terms. What is the main observation that you have? In fact, what is the main difference between these two terms? Sorry? Yes, but much more important than that. What don't you see in the first term? Time dependency, t, right? So the first one is time independent. How about the second one? Is time dependent, right? Okay. Now, pay attention that the first term is just a number, right? It doesn't have t dependency, so it's just a number, some value, 5, let's say. But the second term is a function of time. It's a cosine function. So here is my question. If you remember the first time I introduced the general form of a sine function or cosine function, it was amplitude times cosine omega t plus some phase plus some constant value. What did we call that constant? That was added to the cosine function and it could shift it up or down. Say, what was it? Lecture 21. See, you have a cosine function or sine, doesn't matter. What is the product, what is the thing that is being multiplied by sine? It's called amplitude. Inside the parentheses, you have omega, t, phase. And what is the term that is completely separate from the cosine and is just added to the cosine and it could shift it up or down? It's called the DC value. You remember I called it VDC, okay? It only could shift it up or down, okay? DC value. The reason it's called VDC here is because your original signal is voltage. But if your signal is power, instead of calling it VDC, I can call it PDC, for example, or DC power. Similar to that, can you give a proper label to the second term? AC power. What does it mean? What have we established so far is that instantaneous power is made of two terms, the DC power and the AC power. DC power is time independent and AC power is time dependent. Okay? Let's just plot something so you understand what I mean by that. Okay? Let's assume that this is your power. Now, based on this, can you tell me what is the DC part of this signal?
The value is the y.
Sorry?
Is it the value on the when t is 0?
No.
No.
Sorry?
Not on
I don't understand.
there? Is it not on there?
Which means it is? 0. Can you see that the DC part of this is 0 or no? Is your cosine function symmetrical about the horizontal axis or no? It is. So look at the positive peak and the negative peak. They are at the same value. So it means that it is completely symmetrical about the horizontal axis. So what is the DC value now? 0. What happens if I add some positive DC value to this signal? Right? It will become something like this. Right now, it's not symmetrical anymore. Now, this is called, I mean, it doesn't matter that much, but this is called the positive peak. This value is the negative peak. Now, do you agree that before shifting it up, the average of the signal, let me move it one more time to 0. When it was here, what's the average of this signal? 0. Because whatever you have above the horizontal line, you have the same value below. So they cancel out, the average is 0. But do you agree that because of the DC part, right now the average of this signal is not 0? In fact, the average of this signal is somewhere here, P average. Now this is my conclusion. Do you agree with this statement? The DC part of the instantaneous power is actually your average power. Everyone? The DC portion of the instantaneous power, PT, is average power. So the cosine part is responsible for the fluctuations of power, but the DC part is responsible for the average. I'm going to ask this one more time. Which term is contributing to the average? Only the first term. So let me ask this question in another form. What is the average of the second term? 0. In fact, if you just look at here, I will talk about it in a moment, but the average of any cosine or sine function that doesn't have a DC portion over one period is equal to 0. Over 2 period, again, 3 period, n period is equal to 0. Okay? I'm going to come back to this. Now, one thing that I've already mentioned, what does DC stand for? Direct current. But we use DC not only for current, for voltage and power too. Okay? DC and AC are general terms. Now, for example, what does this signal look like? So you have a cosine function, but instead of starting at, instead of fluctuating or oscillating about 0, it's oscillating about 3. something like that, okay? So it's oscillating between 4 and 2, and the average of the signal is at 3. What is the amplitude of this cosine function? 1. Remember, amplitude is 1. Amplitude is always the number that is multiplied directly by cosine or sine. Now, the concept of averaging is a mathematical concept, nothing to do specifically for electrical engineering, okay? How do we average any function? Any function. For example, if I ask you to average a function over a specific period of time or a specific interval of time, I want to avoid using the period here because I don't want you to think that only periodic signals have average values. Okay, over a duration of time, for example, 0 to 10 seconds. You integrate the function, whatever function you have, and then divide it by 10 seconds. It will give you the average value of that. Okay? So integrate the function over the length of the interval and then divide it by the length of the interval. That's the general definition of any averaging, including power. Now, based on my discussion, can you tell me what is the integral of any cosine function over 1 period? 0. How about 2 period? N period? 0. So what's the average of cosine and sine functions over n period? 0. That's why the instantaneous power has an average only if there is a DC part, because the AC cosine part doesn't contribute to making an average for you. Am I making sense so far? Okay, let's apply everything that we have, every knowledge that I have so far, to a specific components and see what happens. Let's start with a resistor. So, this is the phasor equation for a resistor. V bar is equal to R I bar. What is the label for V bar? What do you call V bar? Voltage, phasor. Okay? What do you call R in this context? Impedance. It happens that it is equal to the resistance because it's a resistor. Okay? But generally it's called impedance. And what do you call I bar? Current phasor. So what is the expression for V bar? Sorry? No. Let's say, so what? There's a cosine in the phasor? What's the point of a phasor if we have to carry the cosine with ourselves? Yes. Vm angle theta v. And what is the current phasor? Im angle theta I. I want you to answer this question. May seem very easy, but it's very important. What is Vm? The amplitude or the magnitude of V. Okay? Remember that. And what is theta V? Is the phase of voltage. Okay? We only need the amplitude or the magnitude and the phase. Now, I can break down this equation into 2 equations because that's a complex equation. I can break it into 2. One based on angle, one based on magnitude. If you take the magnitude of both sides, magnitude of the left-hand side is Vm, magnitude of the right-hand side is Rim, the second equation. What is the phase of the left-hand side? Theta V. What is the phase of the right-hand side? Theta I. Hence these 2 equations. Okay? Now, just by looking at the first equation, can you tell me if this is a resistor or no? Just by looking at this guy, can you confirm that it is a resistor or no? Yes. Why? Because they are in phase. The only component that has the voltage and current having the same angle or being in phase is resistor, nothing else, okay? Very good. Now let's plug these two red equations into the general black equations that we got from the previous page, the general instantaneous power term. So can you tell me what is this value? 0. What does that make cosine? 1. What can I write instead of Vm? Rim. And what can I write instead of Im? Vm over R. What can I... Sorry? Yeah, because of the red equation, the second one, Vm is equal to Rim, so I can replace it with that. Okay? What else do I have? What can I write instead of theta V plus theta I? I can write it as 2 theta V or 2 theta I. Now, I'm going to simplify this equation into two exactly equivalent equations, one based on voltage, one based on current. So let's first focus on voltage. 1/2 Vm squared over R plus 1/2 Vm squared over R cosine 2 omega t plus 2 theta v. Okay? Now let's rewrite it, but only using current. It's going to be 1/2 R Im squared plus 1/2 R Im squared cosine 2 omega t plus 2 theta I. These two equations are completely valid. Both of them are taken from the general form, and both of them will give you the instantaneous power of resistors. Now, why did I write it in two forms? What's the difference? Perfect. So do you remember in the first part of the lecture when we wanted to calculate power, what were the two variables that you should that you needed to find? Voltage and current, right? Except for resistors, you only needed one of them. Do you remember that? The same scenario is here. So if you either have voltage or current, you can find the instantaneous power of resistors. If you have voltage, go for the first one. Current, go for the second one. Okay. Now, let me ask another question. What's the average power absorbed by the resistor? Sorry? Which is equal to 1/2 Vm squared over R, or 1/2 R Im squared. Okay? So this is the average power, because that's the DC part. And the AC part is the other part. Okay, so P average absorbed, P average absorbed. Now, I have plotted these in MATLAB. I have plotted voltage, current, and power. Now, it's color-coded, so the blue and red are voltage and current. I'm going to ask a series of questions. First of all, what is your observation when you are looking at the blue and red, the voltage and current? What is something that's just screaming at you? Wavelength. We don't talk about wavelength. They have the same frequency, and more important than that, they have the same phase. They are in phase. Do you see that? They're going to positive peak, zero, and negative peak together. So they are in phase. Do you see that? Is it obvious for everyone? They're going together everywhere. Okay. They have different amplitude. It's not that important. Now let's focus on the green signal, which is power. First of all, what do you notice about the green signal? It's always positive. What else? Or more mathematically correct statement is to say it's always non-negative, because sometimes it is zero. Okay, the frequency of the green signal is 2 times the red and blue. If it is not obvious from here, you should know it from here. Do you see that? 2 omega t. So the frequency is twice. Okay, now, the fact that it's always above the horizontal line, always non-negative, it means that your instantaneous power is always positive, right? Mathematically, is it justifiable for you why it is always positive? Because they go together, the voltage and current. Whenever they are negative, they are both negative. So their product is positive. Okay, and when they are positive, okay. So can you connect the fact that it is always positive to something physical? The resistor always absorbs power. That's why it should always stay above the horizontal line. Okay? Can a resistor supply power? No. So it should always stay non-zero. And what is the average value of the voltage or current? 0. Is the average value of the power 0? No. It's somewhere, I don't know. Probably here. That is P average. Okay? Any problem? Let's do the same for an inductor. Again, the phasor equation, V bar is equal to J omega L I bar. What is the name of J omega L? Impedance, right? Impedance. Now, I can break that into 2 equations. Again, remember, what is V bar? Vm theta V. What is I bar? Im theta I. Now, I can break this into 2 equations. What is the magnitude of the left-hand side? Vm. What is the magnitude of the right-hand side? Omega Lim. That's how you get the first equation. What is the phase of the left-hand side? Theta V. What is the phase of the right-hand side? It's theta I plus 90 degree. Let me change this pi over 2 to 90. You're more comfortable with. So these are the 2 equations that I have. Something from the previous lectures that I want you to memorize. And remember that it will be very useful for the next 2 lectures. In inductors, current lags voltage by 90 degrees. And you know why, because as you can see, the phase of the voltage is 90 degree more, so it's leading, or the current is lagging, okay? So the current lags voltage by 90 degree. We're not going to use that in this lecture, but it's very important for the coming lectures. Okay, let's plug these 2 red equations into the black general equation and see what happens. So what is theta V minus theta I? So what is the cosine? 0. So this is what I'm going to do. I'm going to write again 2 equations, one based on voltage, one based on current. PLT is equal to 1/2 Vm squared over omega L cosine 2 omega t plus 2 theta v minus 90 degrees. That's the first equation. If you were confused what I did, I just replaced Im by Vm over omega L. Well, not this one, because the first term is actually 0. It's actually the second term. How about the other equation? I can write 1/2 omega L Im squared cosine 2 omega t plus 2 theta I plus 90 degrees. What is the difference between these two equations? It means that you don't need both current and voltage to calculate the instantaneous power. You only need voltage or current. You can either use the first one or the second one. Very important here. What is the average power that is absorbed by inductor? Is it obvious? You only have cosine terms. What is the average of cosine? 0. So the DC term disappeared. This is the plot. I'm going to ask similar questions. What is your observation focusing on red and blue, which are current and voltage? What do you see? They are out of phase. By how much? By 90 degrees. How can we say? Look here. See, when blue is 0, red is at maximum peak. That's why we say they are 90 degrees out of phase, okay? Because of that, what happens to the green signal? It's perfectly symmetrical around the horizontal line. And what does that mean? It means the average of the green signal is 0. So the average power absorbed by inductor is 0. Now, something interesting about this behavior is, let's assume that you have some appliance at home connected to the grid, dishwasher, okay? The grid, the power network is going to supply some current and voltage to your appliance, right? And your appliance is going to absorb the energy, absorb the power, and operate, right? And you pay the price of that amount of energy that you've consumed. Now, okay, it makes sense to model your appliance with a resistor. Not exactly accurate, but since resistor always absorb power, it's very natural and it makes sense to model your appliance with a piece of resistor, because resistor receives or absorbs the power from the grid and operate. Now, what if we want to model some inductor into that as well? Let's see if that makes sense. Your inductor, aka dishwasher, is it absorbing power on average from the grid? No? Is that even possible? What does an inductor do if it's connected to the power grid? If it is a pure inductor? Sometimes it absorbs power where the green signal is positive. Sometimes it's supplying power back to the network, back to the grid when it is negative. It doesn't make any sense. Your dishwasher cannot give back energy to the grid, okay? And that is something a little confusing about inductors and, as you will see, capacitors. So right now, the most reasonable assumption in order to model our appliances is to consider them as resistors rather than capacitors or inductors, okay? We will talk a little about this later, okay? But right now, this is the statement as like a summary of this, that the power sometimes absorbed by the load when it is inductive and sometimes supplied by the load. Any problem? The next component is capacitor. Very similarly, we can write two sets of equations for capacitor. So it should be PC. So I have PC equal to 1/2 omega c Vm squared cosine 2 omega t plus 2 theta v should be plus 90. And the other expression is 1/2 Im squared over omega c cosine 2 omega t plus 2 theta I minus 90 degrees. I have 7 different equations regarding the instantaneous power, and that's just the start. That's just start, okay? Because we're going to have many more power terms. So how can I manage to memorize these power terms? We don't. Look at the equations 1, 1 prime, 2, 4, 4 prime. Okay? So 1 is the most general form. 1 prime is the average part of that. And I don't know why it should be a separate row. If you don't know that the first term is the average, why are you taking the third exam? Okay? So, but anyway, it's a separate row. 2 and 2 prime are for resistors. Do you see that? For either voltage or current. And again, in front of them is the average. 3 and 3 prime are for inductors. And again, in front of them, the average is 0. 4 and 4 prime are for capacitors, and in front of it, the average, which is 0. Okay? So you don't have to memorize them. But you have to understand where to use them. Okay? Let's do this example and see what happens. So we have the voltage source, and we want to find the instantaneous and average power absorbed by each element. This is my question. What is the first step? And I need you to understand and do this first step, at least understand what the first step is very, very fast. What is the first step? Take everything into phasor form, okay? By everything, I mean every element, every voltage, every current. So, first, start from Ethan. What is VS bar? Less than 3 seconds. 15 angles 60 degrees volts. Next one, less than 1 second. What's the impedance of 5 ohm? 5 ohm. What's the impedance of 1 Henry? What's the equation? L. You don't have to memorize it. It's also given to you, but What is the omega in this problem? Next. What is the omega, Jonathan? Don't dare say pass. 4. Whatever is multiplied by t is your omega. What is L? 1. So it's equal to J4. Jonathan, again, what's the units of this? What's the units of impedance? Always. Ohms. The 8 ohm is 8 ohm. How about the capacitor? Next one, William.
Capacitor is
Negative J over omega C, which is equal to negative J over omega is 4 and C is 50 milli, which is 200 milli, 0.2. 0.2 comes up, 10 over 2, 5, negative J 5 ohm. That's your circuit. Okay? Now, okay, this is the first step. You have to do it, no matter what you're gonna find in the circuit. Now, what is the question is asking? What is the keyword? What is the Q word that I want you to focus on? Power. You need to find power. And whenever you hear or see power, immediately you need to find either voltage or current. Sometimes both of them. Okay? Let's start component by component and see what we should do. Let's start with the voltage source. For the voltage source, which one do I have? I have the voltage. Okay? So, do I need to find the current as well, or I can only work with the voltage and find the power? Huh? Why? I couldn't have said it better. Is it a resistor? Is it an inductor? Is it a capacitor? No. So you have to go for the most general form. In fact, let me go here. Which equation should be applied here? 1. 1 is the most general form. Remember, 2 resistor, 3 inductor, 4 capacitor. Okay? I need to go for 1. Okay? So I need to find the current. Let's call this current IS bar. And let's see if we can find it. Canon. How do you find IS if you want to calculate the power? Can you just imagine that everything is in this circuit is just the first part of the quarter? All resistors and everything.
V bar minus.
Yeah, we don't have what comes after the minus. But if everything was resistor, how would you find the current that's being supplied by the voltage source? I did not understand what you said. So if I can find the equivalent resistance of this part and then divide the voltage by that, do you agree that it will give you the current? So I'm going to write it like that. What is that? IS bar is equal to. Yeah, that's what I'm about to do. So negative J5 plus 8 in parallel with J4 plus 5. Do you understand what I wrote for the denominator? That's the equivalent impedance, right? It's your turn, everyone. Calculator, please. Give me the value.
One,
1.838 angle 28.65 degrees amps. One question. Did it give you, was it you, Luke? Did it give you in rectangular form or polar form? And you change it to polar by default? Why? Hold on to that. Let's go to the next step and see why. Okay? He changed it to polar, which is very good, but you need to understand why polar is preferred here. Yes, what's your question?
Why is it preferred because the voltage is given in polar?
The voltage is not given in polar. It's given in cosine form. You change it to polar. Right? Any question? Okay. Now that I have IS, I can go for calculation of power. Let me write the equation for power. Remember, the most general form, PVS T, and this is absorbed. Is equal to, this is the equation, if I can write it, 1/2 Vm Im cosine 2 omega t plus theta v plus, oh, I forgot the theta v minus theta I plus 1/2 Vm Im cosine 2 omega t plus theta v plus theta I. This is the general equation. Okay. Now, is the equation missing something? Something related to the first part of the quarter. The way I've written it should give you some hints.
Voltage
Sorry? No. Why? Because the way I've defined IS, it's supplied power, but I'm looking for absorbed power. Okay, so this is your absorbed power. Now, the only thing that remains is plugging in values, and this is an important part. Very easy, but important. And I'm going to go around, please. I can make you to answer, force you to answer, but try not to pass. Think about it and answer, and please, no one else answer the question, okay? So I'm going to plug in values, -1/2. Ross, what is Vm? Can you verbally describe what Vm means? Again, I'm not forcing you to answer. If you're uncomfortable, you can pass. Okay? Samuel. Next. It is 15. What is Vm? Is the amplitude or the magnitude of the voltage. And it's right there. Look at the phasor of the voltage. 15. Okay? Now, next one. Im. 1.838 amps. Cosine. What is theta V? $60 is the phase of the voltage minus, Braylon, what is theta I? No, you shouldn't. It's very easy. Just look at the screen. What was theta V? Phase of voltage. That's why he said 60 degrees. Can you locate I on the screen? Yes, 28.65 degrees. Right? Plus, everything is going to be repeated here. This is negative 1/2, 15, 1.838 cosine. What is omega? 4, right? So twice that is 8t plus 60 degree plus 28.65 degrees. That is in watts. And I'm going to write the final value, negative 11.772 minus 13.7. Why? Why is it 13? Oh, it's fine. Yeah. It should be 30. 85 cosine 8t plus 88.65 degrees. The units is in watts. Did you ask a question, right? No?
I thought you were going to do that.
Okay. So what do you call this part? The average power or DC power. P average absorbed. By what? By which component? The voltage source. What does it mean that it's negative? Your voltage source on average is supplying power, not absorbing. Okay? Any problem with that first part? Now, Luke, can you answer this question? Why are we interested in finding the voltage and currents in polar form?
So you can use it to find the power, all the other.
Which parameters exactly need the voltage and current to be in polar form? Which parameters? Vm, Im, theta V, theta I, right? Do you see these in the equation? Vm and Im. Which one is easier to immediately write Vm and Im based on? The polar form, okay? Okay, what is the next element? Resistor. Do I need both voltage and current or just one of them? Yes, just one of them. Can you tell me which equation in the last page I should go for? Two or 2 prime? Why 2 prime? You already calculated the current coming from the voltage source, which is passing through the resistor. So you have the current, go for 2 prime. You don't have its voltage. P absorbed of the 5 ohm is equal to 1/2 Vm squared over R times 1 plus cosine 2 omega t plus 2. Oh, I wanted to go for current, sorry. 1/2 R Im squared 2 theta I. It's equal to 1/2. R is 5 ohms. Alina, what is Im? 1.838 amps squared times 1 plus cosine 8t plus 2 times, what is theta I next? 28.65. It's equal to, and this is what I have, 8.445 plus 8.445 cosine 80 plus 57.3 degrees watts. What is the average power absorbed by this resistor, 5 ohm? This is P average absorbed by 5 ohm. Any problem? Okay. Next, J4 ohm inductor. Hannah. So I need to find the power of the inductor. First of all, do I need both current or voltage or only one? Only one of them, right? Voltage or current. I don't have any of them right now.
Correct.
How can you find them? Do you like to do nodal analysis when complex numbers are involved?
But you could do a simple calculation.
Unless you can somehow smuggle your math cat into the exam.
I mean, there's a way to do it where it's simplify the math.
How? What is the simplest way to find either the current or voltage of the inductor?
Also, current division of voltage.
Current division.
Are you using simple?
Current division. Why? Do you have IS or no?
Yeah.
Can you just divide it between the two paths? So you go for current division. Next, Chaz, I want you to give me the equation for current division. Let me call this IL. What should I write for current division? Did you say pass?
No, I said, I'll write it down.
Okay.
IL equals total. What's our IS?
IS.
Times over the resistor, right?
First IS times a fraction. Now, what is the numerator?
The numerator is 4J. Right, that's the opposite.
No, 1 over 4j. Oh, you can't. 1 over 4j, yeah. 1 over j4. What is the denominator? Yeah, that's perfect. So IL is equal to IS one over J4 divided by 1 over J4 plus 1 over 8 minus J5, right? This is the way that I usually do it. Just I will write it just so if you're interested in doing current division this way. I use the impedances themselves, not the inverse of them, but you have to pay attention that you should go for the other branch for the numerator. So I'm gonna have 8 minus J5 here, and then 8 minus J5 plus J4 here, because I believe even for the calculator it would be easier to go for that way. But you have to be careful not to get yourself confused. And the value that I have, you're gonna give it to me. Calculator, give me the value. 2.151 angle 3.77 degrees amps. This is what I have. Okay, next question. Tyler, can you tell me which equation to choose, to use? 3 prime, right? Because I have the current and it's about inductors. Perfect. What was it? 1/2 omega L Im squared cosine 2 omega t plus 2 theta I. Is it minus or plus 90? Yeah. It's equal to 1/2. Omega L is 4. Do you see here? Since j omega L is J4, so omega L is 4, right? I've already calculated that. I am, next, I am. What is the value of I am? Next, Preston. 2.151 amps squared cosine 8t plus 2 times. Next, what is theta I? What next? Next. 3.77 degrees plus 90 degrees. It's equal to, I have it as 9.254 cosine 8t plus 97.54 degrees watts. And just give me 1 second. What is PL absorbed average? 0. We didn't need to calculate it. We needed to calculate it anyway because we wanted to find the instantaneous power. But for average, we could have said just right away 0. Okay, because it's an inductor. Now, how could you get a question about the instantaneous power? Can someone tell me? They ask you what is the power. They might not even say instantaneous. They might just say, calculate the power absorbed by the inductor at t equals 3 milliseconds. As soon as you see t equals blah blah, it means instantaneous because it's a function of time. Then you have to find this, plug in 3 milliseconds, and it will be your answer. Am I clear? Yes.
Why is the current to the inductor not in phase with the current to the voltage?
Sorry again. Why is the current passing through the inductor not in phase with?
IS.
Why should it be in phase?
Maybe the voltage drop goes into- I don't know. That's what that.
Okay, see, the current that's passing through the inductor is just passing through the inductor. But IS is passing through a resistor, an inductor, a resistor, and a capacitor. So it's a combination of components. I can predict what's the phase is, and they're not going to be in phase. Is it making sense? Because, okay, let me ask you this. What is determining the phase of IS? If you remember the mathematical equation, the voltage source and all the components combined, right? But, yeah. And then, what is determining the phase of the current that's passing through inductor? IS together with the capacitor, the resistor, and the inductor. That's why it's changing a lot, so we can't say anything.
So it would be in phase with its own voltage drop.
No,
Correct?
no. Is inductor an in-phase component? No. That's why, in fact, no, we don't have the voltage of the
But it
inductor.
would be 90 degrees off.
Yes. Yeah. So let's just ask this question now that you brought it up. What is the phase of the inductor? What is the phase of the inductor current? 3.77. What is the phase of the inductor voltage? 93.77. Right? I added 90 degrees to that. Where did I get that from? From here. Theta V is equal 90 degree plus theta I. Right? Next component. What is the time? Okay, this is what I did the previous section. Let's do it here again. I believe that right now, finding the power, the instantaneous power of the 8 ohm and the capacitor is quite a straightforward, right? For everyone? So let's do the rest of the lecture. If I have time, I will come back and finish this exam. Yes?
Where does the, so we established like AC current, that the averages are 0 for most of them, but why is, for the resistor, why does it have an average if we're only dealing with alternating current? Where does that phase like shift go, like come from? You know, is that a dumb question?
Yes, but I'm guessing you're not interested in my mathematical answer.
It's to do with the capacitor and the,
No, I mean, even if you didn't have any capacitors or inductors, they're still going to provide some power to the resistor, average power. Even if you have one source and one resistor, it's going to give it some power. Here is the reason for that. You're interested in physical answer, not mathematical, right? Because the mathematical, okay, let me give you the mathematical one. So you have some voltage, and the average is 0. But if you square it, then the average is not 0 anymore, okay? So that's the mathematical answer. What's the physical answer? So what's the meaning of a sinusoidal voltage or current? It means that sometimes it's going from left to right through the resistor, sometimes half period is going from right to left. But does it matter for the resistor? No, because in both scenarios, it's going to absorb. So do you see where the non-zero average comes from? Whether it's going from left to right or right to left, the resistor is a consumer. It's going to it's going to dissipate power, and that's why the non-zero average comes. Okay, let's go, let's skip this page, go to the next topic, and I will come back to that. Okay, let's skip the first 4 or 5 lines. I will come back to this after I explain the concept. Okay, that's the textbook definition, but I first want to explain this to you. Okay, so very simple circuit, just a sinusoidal, not even sinusoidal, some periodic voltage source, okay, VT. The only thing that we know about that is that it is periodic with a period of T, okay? And it's connected to some resistor. Who's next? Red. You're next, right? Yeah. What is the power absorbed by the resistor? And remember, this part is actually the first line, nothing to do with the third section of the course. It's just first part. What is the power absorbed by any resistor if I have the voltage across it? V squared over R. This is something that we had before, right? So it's going to be V squared over R. Now, what is the average power absorbed by R? I should take the average of that guy. V squared over R, I should take its average, right? So how do I take it average? Because I know the, let's write here the T period. 1 over T, sorry, integral from 0 to T, V squared over R. That's just averaging the signal. Anything new or strange? Okay. Let's box this guy. Pardon me? Oh, sorry, I forgot that. DT, always. Because it's time average. Yeah, thank you for that. Okay, so this is the first circuit. We talked about that. A resistor is excited by a periodic voltage source, time dependent. The period is T, and we just calculated it. Now let's make everything much simpler. Let's just focus on a DC voltage source. And the value of that voltage source, let's just call it V effective, VEFF, okay? Some DC value, 5, 3, whatever. Next, what is the power absorbed by the resistor? Yeah. Now, camera. What is the average power absorbed by the resistor? Yes, always. But let me give you an example. Let's say for the third exam, all of you get 39 on your exam, okay? 39. What is the average of class? 39. So, do you agree that V effective squared over R is a constant value? So what is its average over time? Itself, right? It's not time dependent. Okay, let's box this guy as well. Now, what is the condition under which the resistor R receives the same amount of average power from both sources? When this guy the second box is equal to the first box. Obvious, right? If the second box is equal to the first box, it means that both of the sources, one of them time-dependent periodic, the other one DC, are going to deliver the same amount of average power to the resistor R. Let's set them equal and see what happens. So 1 over t, the integral from 0 to t, v squared over r should be equal to v effective squared over r. Can I get rid of r from both sides of the equation? So do you agree that v effective is equal to 1 over t, integral from 0 to t, v squared dt. Okay, let me try and give you a very user-friendly explanation of this concept. Student-friendly. I have some type of periodic signal as my source. Let's call it VT. Periodic signal. And this is my request. Please create a DC voltage source that delivers the same amount of average power to the load as this periodic signal. How do you calculate the value of that DC source? Using that question. Did that make sense? So technically what I'm saying is that you have some sort of periodic signal. What does it mean? It's time changing, right? It's changing by time. Now, I'm asking you to create a voltage source which is giving the same amount of average power to the load as the periodic signal was giving, okay? And this is how you find the DC value. Let's see the textbook definition. Effective value of a periodic signal is a DC quantity, a value that is time independent, which we call it V effective, that delivers the same amount of average power to any load. Okay? Why is it important? Why do we care about the effective value? Because in technical electrical engineering, the one that is not academic or scientific, the one that deals with, for example, making the electrical connections in residential areas or industrial areas, okay? The guy who's responsible to fix things might not even know what sine wave is, right? You don't expect a very experienced, I'm not saying this in any sort of insult, but a very experienced electrician might not know what a sine wave is, but you might be able to fix every problem with your electrical network, okay? So when they are dealing with the power coming from the power outlet, from the grid, okay, they need a number to work with. For example, they want to understand how to model this in their diagrams or whatever, so that it delivers the power that they want to the load, okay? So instead of forcing them to learn the periodic function, the sinusoidal function, we just create one value, V effective, that's supposedly delivering the same amount of power to the load. Am I making sense? For example, what do you call, how much is the voltage coming from this power outlet? 120, right? You all know that. Is it 110 or 120? I don't exactly know. One of them, 110 or 120. Some or around the world is sometimes 220, 120, 110, whatever. Now, what is that 120? So, let me ask you this question first. Is the voltage or is the signal coming from the power outlet, is it DC or AC? Do you all know that it's AC? It's alternating. It's not a fixed voltage, okay? So it's an AC voltage. So what is that 120 representing? Is it the amplitude? It's actually the effective value of them. Meaning that instead of forcing the electrician, the old electrician gentleman that is working with this, instead of forcing him to understand what the amplitude or whatever or the frequency of that is, he can in his brain replace the whole AC thing with a DC voltage source which has the value of 120 volts and do his work. Okay, that's why we call it effective value. Am I making sense to everyone? So you technically will replace the whole thing with a DC source. Now, probably much more common term for effective is RMS. And where is it coming from? R is for root. M is for mean. What does mean mean? Average. And then, what was the other one? S for a square. Okay? So RMS is actually root mean square. Okay? So instead of V effective, sometimes we call it V RMS. Does it only apply to voltages? No, it can be applied to currents as well. So I want you to remember what you do in order to calculate the RMS value. First square it, then mean it, then root it. Okay? Any problem with that? Pardon me?
It tells you the voltage of the standard outlets.
I did not understand whether that was a question or a statement. Okay, yeah, thank you. Now, let me ask a question. I love questions. What is the amplitude of the signal that you receive from the power outlet on the wall? Well, you can't answer that question. Let me give you two options. 120 volts, not 120 volts. Not, okay? That's not the amplitude of that guy. That's the RMS value. That's the effective value. We're going to calculate that in a little bit. Okay. Now, it is asking us this question, the next example, to calculate the RMS or the effective value of these signals. We have three different signals, voltage, current, voltage. The first one, what is the condition for some signal to have an RMS value? It should be periodic. Not necessarily cosine or sine, just periodic, okay? So, I've already written this, but is it obvious that the period of the signal is 5 seconds? Because after 5 seconds, it starts repeating itself, okay? And I've also written the multi-expression of the function. Between 0 and 2 is 8 volts, between 2 and 4 is -2, between 4 and 5 seconds is 0. So I have the function, I have the period, I have the formula. Let's calculate V RMS or V effective. One question. Since V effective is dealing with integral, and I have the plot, instead of having to calculate the integral, can I just go for the areas or no? Can I deal with the area instead of integrating or no? Again, can I deal with the area instead of integrating? Why not?
I think you're good.
Say it. Because it's the squared function. See, that's one of the common mistakes of students. See, V is given to you. You cannot calculate the area. And please, please don't do this. Don't calculate the area and then square the area. Okay? That's not going to work. So just forget about the area for this specific problem. The first one, let me write the equation. So VRMS is equal to 1 over t, integral from 0 to t, Vt squared dt is equal to. What is the period? It's 1 over 5. Integral from 0 to 5. No, I'm not going to do it 0 to 5. Why? Because it's 3 different integrals. I can do piecewise, right? That's easier to do piecewise. I don't have a single expression of the function over the range of 0 to 5. So this is what I'm going to do. From 0 to 2, what is the function? 8 squared dt. Then I have from 2 to 4, negative 2 squared dt. Then I have from 4 to 5, 0 squared dt. Okay, that's equal to. So I have 1 over 5. The first one is going to give you 64 multiplied by 128 plus 4 times 2, 8 plus 0 is equal to, I have the final answer somewhere, 5.215. What is the units of that? Volts. Perfectly volts. But just to make sure the reader or the audience understand that this is based on an effective or RMS value, sometimes we just write VRMS. Okay, just to let the reader know that this is based on an RMS value. But it doesn't mean that it's something new or different. It's the same volts that you've been dealing with. So for the second one, how do you find the effective value? You first have to find what? The line equation. Okay? This is how I find the line equation. I is equal to the slope multiplied by t. Okay? You know how to do that. And it's 2.5 t. Now we have to integrate that, the squared version. So IRMS for the second signal is equal to 1 over t integral from 0 to t I squared dt is equal to, what was the period is 4, 1 over 4 integral from 0 to 4. The function is 2.5 t. Don't forget the square. This is the most common mistake. You forget to square the function. And it's equal to So I have 6.25 divided by 4 multiplied by t to the 3 divided by 3 from 0 to 4. I can trust you can do the same. You can do the rest. So 5.774 amps RMS. I think even your calculator can do some at that point. Okay, so now the third function, very, very important. The third one, the most important one. It is asking you to calculate the RMS or effective value of a cosine function. So VRMS is equal to 1 over t, integral from 0 to t, cosine, sorry, I forgot, Vm, cosine omega t plus, is it phi, v dt. What did I forget? Square. So I have 1 over t. Can I take Vm out of the integral? Vm squared, yes. And then the integral is from 0 to t. It's going to be the integral of cosine squared, right? Can you do cosine squared integral? I can't. I can. Oh, you can do it for you? Yeah. Okay. But, like, what is the term used? Indefinite integral. Can it do indefinite too?
Oh, not indefinite, no.
No, indefinite. So you cannot do it directly. You usually use trig identity to deal with cosine squared. So you can write it as 1 plus cosine twice the angle divided by 2. That is what we used to do in our math courses. 1 plus cosine 2 omega t plus 2 phi v divided by 2 dt. Okay? Now, I'm going to ask you something. Remember, I got rid of the squared. I changed the product to sum. Now, what is the integral of a cosine function over 1 period, 2 period, 3 periods? Anyone remember? What is the integral of a cosine over 2 period? 0. So if I break that integral into 2 integrals, one is cosine, the other one is 1/2, the cosine part will completely go to 0. Okay? We can write and see it, but it's just a waste of time. So from the integral, the only part that remains is 1/2. So this is what I'm going to get. 1 over t, Vm squared, integral from 0 to t of dt over 2. It's equal to. Now, what is the integral of dt? From 0 to capital T is going to give you capital T, right? 1 over t, Vm squared, t over 2. Vm squared over 2 Vm over root 2. A super important result. V effective or Vrms is equal to amplitude over root 2 or 0.707 times amplitude. My last question. What is the amplitude of the signal that you get from the power outlet, from the wall? What is it? Give me the value. 120 multiplied by root 2. That's going to give you the amplitude, right? Any problem? Do you want me to finish this? That was a very fast no. Anyone want me to finish that example, or you just want to refer to it after I finish this? I can just copy from the previous section, okay? You're fine with that? Okay. Just give me 1 second, please. Okay, I think we're done.